Alright guys, so in this video we're going to go through simplifying some trig expressions and proving trig identities with our trig identities that we introduced last class. What we're going to do in this video is going to be a little different though. I'm going to go through and do B and E from page 5 of simplifying trig expressions, and then I'm going to go through and do B and C from page 6 of proving trig identities, and I'm going to do them one at a time. So basically what we're going to do is we're going to go through and talk about some strategy first with regards to a simplification or a proof, and then I'm going to let you guys try it, and then I'm going to show you how I would do it, and we'll talk through it just a little bit. But because this is set up a little bit different, you guys might want to fast forward through this video a little bit to suit where you are with your simplification or proving of these trig expressions. All right, so right here, first off with D on page 5, we've got cotan squared over secant squared theta minus sine squared theta minus tan squared theta. And if I'm looking at this expression, what I'm seeing is squared trig functions being subtracted in the denominator. And so what I want to think here is, can I get to a Pythagorean identity that's going to allow me to substitute one trig function for two trig functions and condense down the expression that way in the denominator? And once I've got maybe one trig function or at least the multiplication of trig functions in the denominator, I can then go through and change everything to sine and cosine. So that's how we want to start thinking about D. So I'm going to pause the video here and let you guys give this one a shot. All right, guys, so first off, what I did when I was looking at the beginning of D is I said I've got squared trig functions being subtracted in the denominator, and I wanted to see if there were any trig functions that were related with a Pythagorean identity. And of course, secant squared theta and tan squared theta are related with a Pythagorean identity. So I shuffled the terms in the denominator to get secant squared theta minus tan squared theta minus sine squared theta, dividing cotan squared theta. And right here, I was able to look at secant squared theta minus tan squared theta and say that if I go from our 1 plus tan squared theta equals secant squared theta, I can get that secant squared theta minus tan squared theta by subtracting tan from both sides, which is going to give me secant squared theta minus tan squared theta equals 1, right? So I made that substitution right there. I substituted 1 for my secant squared theta minus tan squared theta right there, and that gave me cotan squared theta being divided by 1 minus sine squared theta. Then for 1 minus sine squared theta, I took the first Pythagorean identity of cosine squared theta plus sine squared theta equals 1, and subtracted sine from both sides to get cosine squared theta equals 1 minus sine squared theta. And I was able to make the substitution there of cosine squared theta for 1 minus sine squared theta, so that gave me this next step right here. From here, what I did was I said I've got everything in terms of multiplication and division, so I'm going to change everything to sine and cosine. And so right here I had cotan squared theta changing to cosine squared theta over sine squared theta. And what I did right here was I said, instead of a division of cosine squared theta, let's make that a multiplication of 1 over cosine squared theta. And here I can see that my cosine squareds are going to cancel, right? Another thing we could do here is we could sort of consider this cosine squared to be over 1, and then I'm dividing by a fraction, which is the same as multiplying by the reciprocal. So that's another way to see it. Now right here, our cosine squareds cancel, which gives us 1 over sine squared theta, and this whole expression condenses down to cosecant squared theta, right? So that's the condensed expression. All right, guys, so looking at E right here, we've got a trig expression that can be very quick to simplify, or it can take a longer time. So right here, we've got our secant theta plus secant theta tan squared theta. We're pretty close to a Pythagorean identity in the sense that we've got our tan squared and we are adding, right? We have, however, secant in both of our terms, right? So in order to get to a Pythagorean identity, we're going to need to see addition or subtraction of 1 and squared trig functions. So one thing we could think to ourselves is there a way for me to see just tan squared and then plus something else? Another thing we can do is if we're seeing an expression where we can't immediately get to a Pythagorean identity, is change things to sine and cosine and see if we can get things to condense down for us. So right here, what we're going to do is pause the video. I'm going to get rid of some of this extra work over here so that we've got a little bit more room to work. And we'll probably talk about 2 strategies here, but you guys go at it in the way that you feel most comfortable. Okay, so we're pausing the video. All right, guys, so we're going to look at 2 methods of getting to our condensed expression of secant cubed theta here. First, we'll look at the long way. Right here, if I wasn't sure what to do with this expression, I can always change things to sine and cosine and see if I can sort of shake up the expression and get things to condense down. So right here, immediately we've got 1 over cosine theta plus 1 over cosine theta times sine squared theta over cosine squared theta. Right here, we can multiply these 2 guys together and get 1 fraction, giving us sine squared theta over cosine cubed theta. Now, one thing I could do to condense this expression is make it 1 fraction. So if I multiply it by cosine squared theta over cosine squared theta with my 1 over cosine theta, I can get cosine squared theta over cosine cubed theta plus sine squared theta over sine cubed theta. Now I've got common denominators, so I can write this as cosine squared theta plus sine squared theta over cosine cubed theta. This right here is our first Pythagorean identity, so we can say that cosine squared theta plus sine squared theta equals 1. And we've got 1 over cosine cubed theta, which gives us secant cubed theta. The faster way to do this is to say, if I look at this expression and I want to see just tan squared and maybe plus some other term, I can see that secant is a multiple in both of my terms here, and I can factor it out. And when I do that, I've got 1 plus tan squared theta, which of course is secant squared theta. So that's secant theta times secant squared theta, giving us secant cubed theta as a condensed expression from our original trig expression there. All right, guys, so let's take a look at the next page. Right here, we're going to take a look at our second 2 proofs. In looking at these 2 guys, again, we're going to talk a little bit of strategy. So we'll start with B. We're going to do that one out first. Right here, again, I've got a squared trig function and the subtraction. So I should be thinking about a Pythagorean identity to get me to 1. Now, immediately right here, this is not a squared trig function, but we might think to ourselves, is there a way I could get this to be a squared trig function? And right here, the squared trig function that we kind of like to see is the one that's associated with tan squared in a Pythagorean identity, which would be secant. We already have 1 secant there. So that's the angle at which I would take to going into this. Again, if you're unsure, you can always change everything to sine and cosine and see if stuff will sort of flush out for you. In general, it always should. I mean, we're never going to get a situation where one side doesn't equal the other, but in terms of going from one side to the other, there are different roads to doing that. So right here, why don't we pause the video and we'll take a look at this in a second. All right, guys, so looking at this one, what we have is our secant x over cosine x minus tan squared x, and we're trying to show that that equals 1. Right here, I know that 1 over cosine equals secant, and if I can get 2 secants to be multiplied, that will give me secant squared, and there I might be able to get to a Pythagorean identity, since tan squared is the trig function that's associated with secant squared in a Pythagorean identity. So right here, what I did to make this a little bit easier to see is I took that secant x out of the numerator, and I got 1 over cosine x times secant x for this term right here. And then right here, I changed that 1 over cosine x to a secant x in my next step, which gave me secant times secant minus tan squared. Then right here, that's secant squared x minus tan squared x. And if we go to the Pythagorean identity involving secant and tan, we can get to this expression by subtracting tan on both sides, which of course gives us 1 equals our secant squared x minus tan squared x, and that is what this equals in the end. All right, So that one was pretty quick, and obviously there are other ways of doing it that might take a little bit longer. We can investigate those in class more if you guys are sort of wanting to sort of explore those, but this was the fastest way to do it. Okay, so in this next one, we're confronted with a proof that is giving us squared trig functions to start with being subtracted, but they're not trig functions that are associated with a Pythagorean identity. So when we're looking to show that our subtraction of squared trig functions equals this multiplication of squared trig functions, we can't just use a Pythagorean identity directly. In this case, what I would recommend is starting on the left side, you should change everything to sine and cosine and see if you can get two terms to become one term with common denominators. And that's how I would start going about this one. All right, guys, so we'll pause the video here and we'll come back and look at this in a second. All right, guys, so taking a look at this last one, we've got our cotan squared theta minus cosine squared theta. So initially we said we were going to change everything to sine and cosine, which we did here, giving us cosine squared theta over sine squared theta minus cosine squared theta. So right here what I said was I was going to get common denominators, and I did that by multiplying sine squared theta over sine squared theta to my cosine squared theta here. That gave me cosine squared theta over sine squared theta minus cosine squared theta times sine squared theta over sine squared theta. Now I can bring all this together into one fraction, and in that fraction I've got cosine as a factor of both terms in the numerator. Now in my target expression, cosine squared theta is a multiple of the target expression. So in general right here, if I've got cosine squared times an expression, I'm closer to that target expression that I'm looking to get to right here, right? So what I did was I factored cosine squared theta right out of the whole fraction so that I had this piece of my target expression already set aside. Now the rest of this should equal our cotan squared, right? So right here, I've got 1 minus sine squared theta in the numerator. That I can show with the Pythagorean identity equals cosine squared theta. So I made that substitution. Now right here, we've got cosine squared theta over sine squared theta for that second multiple, and of course that equals cotan, so we hit our target expression. Now there is a faster way to do this from this step, and that is to say, right here, I know that cosine is a part of my target expression, and if I cut this off, if I didn't worry about getting common denominators, I could immediately get that as a multiple if I factored it out of both of my terms right here. So I would have cosine squared theta times 1 over sine squared theta minus 1. And then right here we'd have cosine squared theta times, and then right here 1 over sine squared is going to be cosecant squared theta minus 1. And of course this equals cotan squared when we do a little bit of manipulation with that last Pythagorean identity. So we'd have cosine squared theta and then times right here cotan squared theta. So just a different way of looking at it. In general right here, this is what I thought most of us would think to do, and so I stuck with that one first. But there are some shortcuts in these, and there are multiple ways to get to these proofs, but in general we want to make sure that we're sort of taking one side of the equal sign and showing all the steps to how to get to the other side. That's how we do this. All right, guys, so that's this video. We're going to stop this one here, and we'll have one more video in the homework.